In this section, we're going to talk about first order linear differential equations. So when we talk about something that's a first order linear differential equation, first order means the highest derivative that we have is a first derivative. Linear, if you remember, means that we have functions that are in terms of just x here, here, and here. So when we have a first order linear differential equation, we can write it this way. Now, to put this in what we like to call standard form, we would want to divide every function or everything by this a sub 1 of x. And if we were to do that, just to write some notation here, then we would end up with dy over dx. Notice we've got that 1 that's in front there. And then we're going to have another function here. I'm going to call it p of x. If I take a function and divide by a function, I get a new function. And then I have a function divided by a function here. It's going to give me a new function. I'm just going to call it f of x. So we really need a first order linear differential equation to be in what I call standard form in order to go about solving this differential equation. Now, if you've taken Calc 2, you probably saw a formula that went along with that. I'm going to talk about where that formula comes from. I do not want you to memorize formulas. I want you to understand the process of what's going on behind the scenes. So, back in Calc 2, Larson's textbook, which is the one that we use here at Mitchell, talks about this in section 6.5. I'm calling that function f of x. They gave you a formula that said, here it is. All you have to do is figure out what your p of x is and plug everything into your formula and then integrate those sides. And then to solve for y, we would divide by that exponential function there. I want to show you where that's coming from. So there's our standard form. So what we really want to do is multiply by something clever. And if we were to multiply everything by e to the integral of p of x dx, and I'm just going to call this function u of x so I can reference it later. Or we could just call it u for short. So if I multiply everything by this, if I multiply this by that, I'm going to end up with this guy. I'm going to use y prime instead of dy over dx just to make notation a little bit easier to see. So we would have that. And what's neat about this is that this guy is actually a derivative. If we were to take y times e to the integral of p of x dx, and we were to take the derivative of that. Okay, remember what this notation means? This notation means that you want to take the derivative of whatever's inside of here. So if we were to take the derivative of this guy, that would be a product rule. Product rule would say it's the first function times the derivative of the second. So we would have y times the derivative of e to the integral of p of x dx. And if we were to find the derivative of that e function, we know the derivative of e to the u is e to the u. And if we take the derivative of that exponent, when we take the derivative of something we want to integrate, we can think about that second fundamental theorem of calculus, and that will give us just that p of x. So using the product rule, first times derivative of the second actually gives us that piece. Plus second times derivative of the first So if we take the second function times the derivative of y, we would get that piece. So you can see easily how this is the same thing as that left-hand side of the line above it. So we're just rewriting this. It's just a clever manipulation we're using here. So now that we've done that, we could multiply both sides by dx, and then we could integrate. Now, when I integrate something I want to take the derivative of, I'm left with what's here. It's that second fundamental theorem of calculus that we're using. And then I would need to integrate this right-hand side, which, we don't have any functions, so I'm just going to leave it in this notation. So that's where that formula from Calc 2 is actually coming from. It's coming from this idea that we can multiply both sides by this exponential piece. And like I said before, I don't want you to memorize equations. Don't memorize this guy. Instead, understand the process that's going on here. So let's look at a few examples. First question you got to ask yourself is this written in proper form? And the answer is yes, we are written in proper form because we have a 1 in front of that dy over dx. So it's meeting that requirement that we have dy over dx, or we could say y prime, minus some function in terms of x times y is equal to some other function that I'm calling f of x. So the first thing is we need to figure out what are we going to multiply this equation by, and that's what we're going to call an integrating factor. That's our u of x. So we need to identify the integrating factor. So it's always going to be e to the integral of p of x. Our p of x is negative 3. So when we integrate negative 3 dx, we're going to get e to the negative 3x here. And then once you find that integrating factor, then we're going to multiply through. So if I multiply this equation by the integrating factor, I get e to the negative 3x minus 3e to the negative 3x times y. Don't forget the dy over dx is equal to 0 times e to the negative 3x, which is 0. The whole reason we do that is so that we can rewrite this guy. So this is always going to be your integrating factor times y. That's what we want to take the derivative of. Now, this is a great place to check your work. Because for this to be a true statement, this e to the negative 3x times y, the derivative of that has to equal that line above. If it doesn't, then there is something wrong in your problem somewhere. Remember, the notation means you want to take the derivative of what's inside. So if we want to take the derivative of this, that would be a product rule. So it would be the first function times the derivative of the second, which is y, plus the second function, y prime, which is y, times the derivative of the first, which is e to the negative 3x, times the derivative of the exponent, which is negative 3. So do you see how this guy is equivalent to this? And now that we have that, if we wanted to integrate, we can multiply both sides by dx. And then we can integrate both sides. If I integrate something I want to take the derivative of, those are opposite ideas there. So we are left with just that integrand, e to the negative 3x times y. When we integrate 0, we get 0 plus c. And then, ideally, you want to get y by itself. So let's divide by e to the negative 3x. So we're going to get y is equal to e to the positive 3x times your constant c. So let's talk about the steps that we did here. The first step is to make sure the differential equation is written in standard form. Then you want to identify your integrating factor. And that's what we called u of x. So after you do that, you're going to multiply through. And then after we multiplied through, we did a rewrite. And we actually rewrote this step in terms of a derivative. That's also a great place to check. If this step is not equivalent to what you had above, then there is something wrong in the problem somewhere. So after we did that, we integrated. And that's what we did in this step. And then if it's possible to solve for y, then we can write this explicitly. If not, then that's fine too. I've had a lot of students over the years ask me, how do I know where to stop in the process? And it's one of those, beauty is in the eye of the beholder. So with this one, super easy to solve for y. You're going to want to solve that guy for y. If we would have ended up with something weird like a y squared, you don't want to solve for y in that case. It just depends on whether or not you can solve for y. So let's look at another example. Let's say we want to solve this one. Now this guy is a little bit different because instead of having a 0 here, we have a 6. So our final solution is going to look a lot different than what we had before, but the process is still the same. So we're going to start with identifying that integrating factor. So in this case, it's going to be e to the negative 3x again. Then we're going to multiply through. And when we multiply through, we're going to have e to the negative 3x times dy over dx minus 3e to the negative 3x times y. And that's equal to 6e to the negative 3x. After we do that, we're going to do our rewrite. We're going to rewrite this left-hand side. It's always the integrating factor times y. But you should always check to make sure this is written correctly. If this is not correct, your final answer will not be correct. So this is where we're going to do a check. So let's take the derivative of what we said we were going to take the derivative of. Remember, this notation means you want to take the derivative of what's inside. What's inside is a product. So it's the first function times the derivative of the second plus the second function times the derivative of the first. And we can see how this guy is the same thing as what we have here. So we know that this step is correct. That's what the check does, is it verifies that that step is correct. So once we do that, then we're going to do the integration. I'm going to integrate both sides. Technically, what's happening is we're multiplying both sides by dx. When we integrate the left, taking the integral of something we want to differentiate, it's going to leave us with that e to the negative 3x times y. When we integrate this side, this is a u substitution. So our u is that exponent e to the negative 3x. du would be negative 3, so we are missing that negative 3 there. We can multiply it in as long as we compensate with a negative 1/3 out here. So we have 1/3, negative 1/3 times 6, which is negative 2. And when we integrate e to the u, we get e to the u. And then plus c. So now let's get y by itself. We're going to divide by e to the negative 3x. So we're going to get y is equal to negative 2 plus c e to the 3x. So there's our final answer. If we wanted to talk about domain for this problem, or where is this solution valid, this solution would be valid everywhere. If we go back to that original differential equation, there's no exclusions for x. And if we look at that solution, there's no exclusions for x there. Even when we were dividing everything by e to the negative 3x, we know exponential functions in that form are never 0. So there's no exclusions, which means that this would be fine everywhere. The solution is valid on all real numbers. And in fact, the same thing is true over here with this one. We could say that the solution was valid from negative infinity to infinity. Let's look at another one. Our first step is to get this into the standard form that we need. So we're going to divide everything by x. So we're going to have dy over dx minus 4 over x times y is equal to x to the 5th times e to the x. So notice that in this case we had to divide by x, which means that we have already introduced a domain issue, because when we divide by x, we know that the denominator can't be equal to 0. So let's keep track of that over here. We know x can't be equal to 0. Domain has to work for, I like to say, every piece of the problem. So anytime you start dividing by things to get it in standard form or proper form, anytime you get that final solution, you have to think about any kind of issues where the differential equation wasn't defined, which in this case it won't be defined as 0, or issues where the solution may not be defined. So we're going to keep that in mind as we go through the process. The process is the same. We still need to find that integrating factor. It's going to be e to the integral of negative 4 over x dx. And then when we integrate that, we're going to get e to the negative 4 ln of the absolute value of x. But remember that negative 4 is really an exponent on that x. So at this point, it is okay for us to drop the absolute value, because if I take something and I raise it to an even power, then I'm always going to get a positive. And remember, that's why the absolute value is there to begin with the ln function, is it forces whatever you're taking the ln of to be a positive value. And then if we were to use log rules to simplify that, we know e and ln are inverses of each other, so we get the argument x to the negative 4. So there's our integrating factor. Then we're going to multiply through by that. We're multiplying this guy through. So then we're going to do some simplifying. This is minus 4x to the negative 5 times y. That's equal to x e to the x. So now we're going to do our rewrite step. Let's rewrite this guy. It's going to be the integrating factor, which is x to the negative 4 times y. You always want to check it. So I'm going to check it over here on the right-hand side. Is this equivalent to this? That's what we're asking. So if I were to take the derivative of what's inside the brackets, first function times derivative of the second plus second times the derivative of the first. Is this equivalent to this? The answer is yes, so we know we have integrated that properly. So now we can go to our integrating step. Technically what's happening is we're multiplying both sides by dx, and then we're integrating. When we integrate something we want to take the derivative of, we're left with that, what's inside the bracket, which is x to the negative 4 times y. This is going to require by parts. So we need the formula for by parts. We need to figure out what u is going to be and what dv is going to be. In this case, u is going to be x. dv is e to the x times dx. That's going to tell us what du is, because du is just the derivative of u. That tells us what dv is going to be, because v is just the integral of dv. So when we integrate, we're going to get uv minus the integral of v times du. And if we integrate e to the x, we get e to the x. So this right-hand side becomes x e to the x minus e to the x plus c. Don't forget the plus c, it's super important. So now to get y by itself, and we can solve this one for y, that's why we're going to do that. We're going to divide each piece by x to the negative 4. So once again, we've introduced a domain issue of 0, but we already said we had to exclude 0 anyway from the solution. So this is going to be x to the 5th times e to the x minus x to the 4th times e to the x plus c x to the 4th. So if we're talking about where is this solution valid, this solution is not valid at 0 for reasons that we stated previously. So we could say it works on 0 to infinity. As long as we're not using 0, we're okay. Remember, differential equations have to be continuous on an interval. We cannot say this because it's not continuous on that entire piece, because it's not continuous at 0. So we're going to use just one part of that interval. And I'm just going to choose to use the right-hand part. We could use the left-hand part if we wanted to. Let's look at another one. This is where you may want to pause the video and try this one yourself. So for this one, our first step is to divide everything by x squared minus 9. Put this in that proper form. So now we need our integrating factor. So if we integrate that exponent, that's a u substitution. If u is the denominator, then we would need a 2 there and compensate with a 1/2. So let me show you over here what's going on. That's what we're trying to integrate. This is almost in the form of du over u, which would be a logarithm property. But we are missing the 2 here, and we could compensate with a 1/2. If u is x squared minus 9, then du would be 2x dx. So there's our du. Here's our u. So now we're integrating the 1/2 du over u, which is the ln of the absolute value of u, which is 1/2 times the ln of x squared minus 9. So we're doing a u substitution to solve that. So we're going to have e to the 1/2 ln of x squared minus 9. We could rewrite that. That 1/2 is really the exponent. So x squared minus 9 to the 1/2 is the same thing as the square root of x squared minus 9. And that's going to reduce to square root of x squared minus 9. So now we're going to multiply. Then we're going to do our rewrite. We should always check that. Is this equivalent to this? This is a product rule, so it says the first one times the derivative of the second plus the second one times the derivative of the first. So if we were to take the derivative of this, we would bring the exponent down, subtract 1 from the exponent, and then take the derivative of the inside. So I'm going to do some tweaking here. So that 1/2 and that 2 is going to reduce. So we're going to have an x and a y over the square root of x squared minus 9. So the question is this equivalent to this? And the answer is yes, because this guy would reduce to that. So they are algebraically equivalent, which means we have written that the correct way. So now we're going to integrate. And if we integrate both sides, we're going to get the square root of x squared minus 9 times y is equal to 0. And to get y by itself, 0 plus c, we're going to divide by that square root. So then let's talk about domain. Where is this solution going to be valid? Well, right at the beginning, we said that we had to divide by x squared minus 9. And when we did that, we introduced domain issues. So we know that the domain can't equal positive or negative 3. But we also have issues with that square root in here. And now that square root's in the denominator. So if we think about where would this be valid, this would be valid where x squared minus 9 is strictly greater than 0. Because we need that radicand, that stuff under the radical, to be positive in order to take a square root to get a real value there. So if you think back to how you would solve a quadratic inequality, you first find where that quadratic's equal to 0, which gives us the plus and minus 3, which were issues right off the bat when we divided. And then we would do a sign chart. Let's pick something to the left, and let's plug it in here. If we pick something to the left of negative 3, like negative 4. Negative 4 quantity squared minus 9 gives us a positive. If we pick something in between negative 3 and 3, like 0, we would get a negative. And what that means is that if we're not meeting that inequality, we want values to be greater than 0, not less than 0. So this area is out. If we plug in something bigger than 3, like 4, 4 squared minus 9 gives us a positive. So we're good there too. So we could say that our solution, and notice this is a general solution, is valid from negative infinity to negative 3, or we could say it's valid from 3 to infinity. Okay, now it can't be valid on the joint domain because there are issues in between. These two put together is not a continuous domain, but this piece is certainly continuous and this piece is certainly continuous. So that's why we have to have an or there. And in fact, if we wanted to, we could just say this will work from 3 to infinity. And in fact, we could even verify that domain by looking at the slope field for that differential equation. So we could go to Desmos and the slope field. So here's the slope field generator inside of Desmos. And we have to solve this guy. It says gy of x is equal to the derivative dy over dx. So if I solve that differential equation for dy over dx, I get negative xy over x squared minus 9. And here's our slope field. So I've gone ahead and graphed this solution y equals c over x squared minus 9. And you can see that our slope field has some blanks here, which would be at the negative 3 and at the positive 3. And if we look at that green solution, it's giving us those solutions to the left and to the right. So you can see that the solution, this green piece on the left-hand side, would be the piece that would be defined on the interval from negative infinity to negative 3. The green piece on the right is defined from 3 to infinity. So let's do an initial value problem. This is going to allow us to find that C value. So we're getting a particular solution here. Okay, notice this is already written in standard form or proper form because we've got a 1 in front of that dy over dx. So we're going to start by finding the integrating factor. So we're going to have e to the integral of 1, since that's our p of x dx, which is e to the x. Then we're going to multiply through. We're going to do our rewrite. This is where we would check. So if we were to take the derivative of this, product rule says it's first times derivative of the second plus second times derivative of the first. That is the same thing we have here. So we know that we have written this correctly. So now we're going to integrate. And if we integrate both sides, we're going to get e to the x times y is equal to the integral of this. This guy's going to require by parts. U is x, dv is e to the x dx. So du is going to be dx, and v is going to be e to the x. So this is going to be uv minus the integral of v du. And then if we divide everything by e to the x, we're going to get y equals x minus 1 plus c e to the negative x. So there's the general solution. Now let's look at that particular solution. And let's substitute in that initial condition. Y is 4, x is 0. So we're going to get 5 for C. So our particular solution is this. If we talk about where is that solution valid, let's go back to the beginning. This was already written in proper form, so we did not have to do any kind of division. So we didn't introduce any issues with domain. And if we analyze this a little further, there are no issues existing with domain. The only time we had to deal with something in the denominator was when we divided by this e to the x. And when we did that, we ended up with this last term as 5 e to the negative x. Now, we know that e to the negative x will never be equal to 0. It's an exponential function. So there are no domain issues with this, which means the solution is valid from negative infinity to infinity. Now, we could talk about some asymptotic behavior that's going on with this solution. And we're going to see asymptotic behavior really due to this guy, due to that e to the negative x term. If we were to take the limit as x goes to infinity of that term, whether we look at that general solution or that particular solution, I'm just going to use general, then what's going to happen is we're looking at the limit as x goes to infinity of c over e to the x. So as x gets larger and larger and larger, that denominator is getting bigger and bigger, which means that whole term is going to 0. So we call that term, the c e to the negative x term, a transient term. And this notion of a transient term is usually used in applied problems. So I want to make you aware of what's going on there. So as x gets bigger and bigger, this whole function is really heading towards that line of y equals x minus 1. So if we were to graph this in a slope field so you can kind of see what's going on here, we've got that differential equation, and I've solved it for dy over dx. That would be equal to x minus y. Here's our general solution. And I did graph just the general solution. And let me graph the line y equals x minus 1 on top of it. So the green solution over here on the right is that solution. Notice there's no issues with domain. We don't see any kind of gaps in that slope field, which would indicate an issue with domain. That's why it works from negative infinity to infinity, both the solution and the differential equation. That green is the general solution. I can change that for the c value, and you'll see how it changes. That blue line is the line y equals x minus 1. So you see as x gets bigger and bigger, that green function is approaching that blue line. Okay, that's what it means to have asymptotic behavior, is as we head off to infinity in some direction, whether it's positive infinity or negative infinity, then we approach some kind of line or some kind of other function. Usually we talk about lines with asymptotes, but it could very well be quadratic in nature in a different example. So that's what's going on with that one. And then let's look at one more. Let's look at example 6, where we have an initial value problem. So there's really two pieces going on to this. So we have dy over dx plus y is equal to f of x, but f of x is a piecewise function. That means we get to set up two different differential equations to solve. This is going to work from 0 to infinity. Just kidding. 0 to 1. And this is going to work where x is greater than 1. So we need to set up our integrating factor. Multiply through. Rewrite. This is where you would do the check. If we take the derivative of this, we will get that. So it does check out. Then we're going to integrate. And then I'm going to solve this for y by dividing everything by e to the x. So now let's look at that initial condition. We started with the condition y of 0 is equal to 0. 0 is on 0. The point 0, 0 is actually on that first piece. So we're going to use that condition for this piece of the puzzle, which was on that first piece. So we're going to get negative 1 for c. So we're going to have y equals 1 minus e to the negative x. So now let's integrate that other side. This is the piece for x is greater than 1. Same steps apply, integrating factor. Multiply through. 0 times e to the x is just 0. Do a rewrite. Check. The derivative of that is that. Integrate. When we integrate 0, we get 0 plus c. And then solve for y. So it would be c over e to the x, which is c e to the negative x. So at this point, we really need to figure out what that c value is going to be. And that's where we're going to use the definition of continuity to figure out what the c value would be. We cannot use that initial value 0, 0 because we've already used that for the other piece where that x value was defined. The x value of 0 is not defined for this piece of the puzzle. So that's why we have to resort to that definition of continuity. So if you think back to Calc 1, the definition of continuity really relied on the limit. The limit as x approaches c of f of x had to equal f of c. Now, when we talked about a limit as x approaches c, that really means that left-hand limit and that right-hand limit have to go to the same value. So we're going to use that idea here. And the issue is really happening at 1 because that's where the break is in this function. Is at the value 1. Less than 1, we're here. Greater than 1, we're here. We're trying to figure out the solution for this differential equation. It needs to be a continuous piece. So I know what's happening for the limit. I want to approach 1 from the right. And I want that to equal y of 1. Now, why am I approaching 1 from the right? Because that's the piece I just found. It's on the right-hand side of that interval. If I think about the interval from 0, here's 1 and beyond, I'm asking what's going on at the value of 1. I just found the solution, integrated solution to the differential equation on the right-hand side, but I need the value at 1 to equal that solution. And I know the value at 1 because I know this guy. If we were to plug a 1 in here, we're going to get y equals 1 minus e to the negative 1. And we're going to take the limit as x approaches 1 from the right of c e to the negative x. So there's our y. This is where we're getting the y of 1. Why do we have to use this piece here? Because we know this is valid up to 1. We know the particular solution through there. We want these two pieces of the differential equations to connect. So we're connecting all the dots here, using a lot of stuff really from Calc 1. So if we were to take this limit, it's going to be c e to the negative 1. Oops. Equals 1 minus e to the negative 1. The goal is to find c. Let's divide everything by e to the negative 1. So we're going to get e minus 1 there. So there's our c value. So y is going to be equal to e minus 1 times e to the negative x. So our final solution for this is going to be written in two parts. We're going to have a piece where x is between 0 and 1 inclusive, and we're going to have a piece where x is greater than 1. Between 0 and 1 inclusive, we are here. 1 minus e to the negative x. Past 1, we are here. So there's the final solution to that differential equation.